So last meeting, we discussed section 18.1 and section 18.2. Today, we shall go about with the results without proving them. So before we start with section 18.3. Okay, so this is the assumption. We will observe y1 to yn, which are IID of dimension r, such that each of the yi's are normally distributed with a mean vector mu and a covariance matrix sigma. These are the scopes of the parameters for your yi. And then we assume that sigma is positive definite for the assurance of the existence of an inverse. So some characteristic of an estimator that we had is your sample mean denoted by y bar, which is computed as 1 over n times the summation of the yi's. So each of the yi's here are normally distributed with a mean mu and a sigma covariance matrix. And the S will be the one which is divided by n minus 1, because this will give you the estimator for sigma, which is unbiased. So it should be divided by n minus 1. And we need this transformation, or we write S as a function of the summation of yi prime, because later this is a sufficient statistic, and a y bar, which is the summation of yi 1 over n, will be also a sufficient statistic. We shall use these two components to use the factorization criterion and identifies y bar and s to be jointly sufficient. So we call y bar as the sample mean and s as the sample covariance matrix. So again, theorem 18.1 in Arnold's shows that y bar and s are jointly sufficient, and they are a complete sufficient statistic. So there was a need to rewrite S in terms of the summation of yi prime, and the y bar, of course, is a function of the summation of yi, because that will be used to in your factorization criterion. That is, we can factor the joint density function of your yi in terms of u and v. Okay, so doing the argument of expanding and simplifying the joint density function, we see that we can write the joint density function as a function of u and a function of v. No? So you have u and v, which is u was the summation of yi and v is the summation of yi prime, is a sufficient statistic. And then to show completeness, we had to have a knowledge on the exponential form. I did not discuss the proof of that. Just read about it. And the next theorem tells us that y bar and s are independent, and we can derive the distribution of y bar. So it starts with a yi, which is normally distributed, y bar is also normally distributed with a mean vector mu, the same as the yi, but the covariance matrix now will be equal to sigma over n instead of just being sigma, and S being a function of a quadratic form in y will this time be a generalized chi-square called a Wishart distribution with n minus 1 degrees of freedom and a covariance matrix sigma over n minus 1. There is no delta here because delta here will just be equal to 0. So S will be a central Wishart distribution. So we have shown and discussed the proof of theorem 18.2, which has some subsectioning in the proof. So to show that S is a Wishart distribution, we use the result um, having a matrix which is idempotent, because we can express S in terms of this matrix here, I minus N A prime A. So if you recall, S can be written as this form, Y prime I minus N A prime A Y. So if we can show that this is idempotent, then we can use some previous results, okay, for a Wishart distribution. And then to show independence, we use the result on 17 point theorem 17.7 that talks about uh, showing that AB is 0, and you have two estimators that can be expressed as uh, AY, and the other one is A prime BY, no? And then if we can show that A times B is 0, then these estimators are independent. So we can show that y bar was a function of AY, and sigma is a function of A prime I minus N A prime Y. So that will be your B, and then multiply that to, and that is equal to 0. So since we have shown that it is equal to 0, then the y bar and the n minus 1s are independent. But actually in the proof, what we've shown is y bar prime, but since y bar is a function of y bar prime, so y bar and s are also independent. N minus 1 s is a function of s also, and they are invertible. Okay. The next concept that we studied last time is other properties of your y bar and s. And in this theorem 18.3, we see that y bar is MVUE for mu, s is MVUE for sigma. So when we say MVUE, we show that y bar is unbiased for mu, or that is the expected value of y bar is mu, and S is unbiased for sigma, or that is, we can show that the expected value of S is equal to sigma. To show that y bar is unbiased, by assumption, we know that, or by theorem 18.1, we know that y bar we know that y bar is normally distributed with a mean of mu. So automatically from this result, we can say that the expected value of y bar is mu. However, to show that the expected value of S is sigma, last time, what I have given is just this setup here in your notes. So I tried to make a detailed proof of that. So this is the detailed proof. So here, there should be okay, we can write, okay, by definition of your S earlier, we can write where is my S? Okay, here. So this is S is equal to 1 over n minus 1 times this term here, or S is equal to that. So ibig sabihin, we can write n minus 1 times S to be the sum of these two terms, no? Or we can write n minus 1 S to be equal to this term, yi prime minus ny bar, y bar prime. So we can write this or this one. So in the proof of showing that S is an unbiased estimator, so we can write now n minus 1 times the expected value of S to be applying expectations to be the expected value of that. So this is the first line, no, of how we define S. And then what happened here is we just added in this term here, we added and subtracted mu. Yeah. In this term also, we added and subtracted mu. And then doing matrix operations here. So we can have the primes there, correct? And then the first term here is this one times this one, which is this term. And then what you will have is 3 more terms. We'll have this one with this one, this one with this one, and this one with this one. Okay. Now the 3 terms will be the last term here, this one, will be equal to y bar mu minus times y bar mu prime, and that will be plus. And these 2 terms here, this one with this one, will have a minus 2 something. So what will remain is only one of this form. No, you can simplify that. So it will be something that 2 minus 2 y bar mu and y bar mu prime, then plus one of them, so that will be only 1. No, you can rewrite that. And then if you get the summation afterwards. So I did not write the detail. You can inspect that. That there is some procedure here to obtain this. So after distributing, kining kana with that, kini with this, and this one with that. And applying the summation for each of the term there, what will remain is the first term, kini siya, which is this one. And then after simplifying the three terms, so napakay three cross products din eh. Are you with me?
Yes, ma'am.
Do you understand? Napakay three cross products diha. The other one will be two, duha minus isa, and then getting the summation, which is just a constant with respect to the summation, you will have n there. Anyway, there are two steps to get in this equation there. Two steps more, no? So you can check that. That is just simple matrix manipulation. So after getting this third line here, this time you get the expectation of each term. So expectation of this times the minus the expectation of that. So that is distributing expectations is additive. And then this one is using the property of summations and expectations. So you can have the expectation of the summation to be equal to the summation of the expectations. And n here will be just a constant with respect to expectation. So if you scrutinize these terms here, if you scrutinize these terms there, this is actually the covariance matrix for yi. No? This is the covariance matrix of yi. And then this is a constant with respect to summation. So you will have sa yi man ta na reference. So you will have n there. And if you scrutinize this expectation, this is actually the covariance matrix of y bar. And you know that the covariance matrix for y bar is 1 over n times the summation of times sigma. So what you will have here is n times, this is equal to sigma. So n there will be for the summation sign, which is covariance yi is just a constant over the summation sign. You have an n here, and then the covariance of y bar is 1 over n sigma. So by substitution, you have that. So this is cancelled. So what you will have is n sigma minus sigma. If you factor out sigma, you will have n minus 1 times sigma. So remember, this is n minus 1 s. So that when you get expected of x, so when you want to get the expectation of s squared, so you will have to transfer this. That will be 1 over n times the answer here, which is equal to sigma. So in your notes, what you see was just this setup here. Do you agree? Is that what you see in your notes?
Yes, ma'am.
Okay, so don't worry, I will give, before the exam on Friday, I will give you the most updated PDF file of the lecture notes. So that's it. We have shown that y bar and s are unbiased estimators for mu and sigma respectively. And by the Le-Manchefei theorem, these are MBUs for mu and sigma. Okay, so recall that y bar will be MVUE and S will be MVUE for sigma. So for MLE, y bar is still an NLE for mu, but S will have something like this. So it will be equal to n minus 1 over n times S for an MLE for sigma. So if you scrutinize this formula, that is n minus 1 over n, S is also equal to a summation of something here, no, over n minus 1. So actually, the MLE is the one with a summation, but the divisor is just over n. Okay. So this lemma is useful in finding the maximum where the density is maximized. If we can write your joint density function in this manner, then this density is maximized at a value u equal to 1 over NA. So we saw last time that we use this to show where the joint density of the normal is maximized for the variance. So here, no? So that's why the MLE for sigma is n minus 1 times ns. Okay. So when we talk about being an invariant estimator, estimator has its relationship with a loss function. So generally, we use this Mahalanobis loss function for our loss function, and it is also related to some form of transformation. For it to be a best, then you should have another competing estimator, which is also invariant, but with respect to the variance, it will have the smallest variance. So the transformation that the y bar and s are to be an invariant estimator is only in an additive transformation. So you will have a matrix A times your estimator times some constant B there. So we say that this estimation problem is invariant under this group of transformation if the loss function related to that transformation will still be equal to the original loss function of the Mahalanobis loss function. So if you do any transformation on your D and you get the loss function associated to that transformation, and if you will get the same loss function as the original loss function that you have stated in this particular problem or in this particular discussion, we limit it in this loss function, the quadratic loss function or the Mahalanobis distance loss function. So the next theorem tells you that y bar is the best invariant estimator for mu. So to see invariance, you have to verify this statement. It is invariant if and only if you can rewrite it in this manner. So any statistic passing through this transformation is just equal to A times the original statistic plus B. Okay. So if you can show that, then your estimator is invariant. And then to show that it is best, it should have the smallest risk among all invariant estimators. So when we talk about MBUE, we talk about the minimum variance, but when we talk about the best invariant, it should be the smallest risk. Now, the smallest risk is actually the expectation of your loss function. So basta invariance gani ang imuhang hisgutan, dili ta mo tan-aw sa minimum variance, but we look at the minimum risk. Minimum risk is also referred as the expectation, or what it will be the expectation of your loss function. Are you with me?
Yes, ma'am.
So kung MVOE unsay tan-awon para mabes? Pag MVOE, unsay tan-awon para best siya?
Ang variance, ma'am.
The smallest variance, no? Minimum
Yes, ma'am.
variance. But if it is the best among invariant estimators, you should look at the risk, no? And the risk by definition is the expected loss. So this is the proof of how you computed for the risk of another competing estimator, and we see that the risk of any other competing estimator will be a function of a positive term plus the risk associated with your y bar. Okay, so this is the risk associated with your y bar, and this is the risk associated with other competing invariant estimator. So since this is a positive term here, so we say that the risk associated with other competing estimator, which is this one, is greater than the risk associated when using your y bar. So y bar has the lowest risk and thus will be the best invariant estimator for estimating your mu. But there is another estimator which will be better than y bar, and that will be the start of the lecture now. This is now section 18.3. So before I go with the multivariate case, since we did not pass through the Jamestown estimator for mu in the univariate case, so let me start with the univariate case so that you can easily relate it with the proving when we have the multivariate case. So actually, the Jamestown estimator is chapter 11 of Arnold. So if you recall, we only discussed until chapter 6 of Arnold's, no? So let me go back with chapter 11 of Arnold. So this section derives some alternative estimator for mu that are in some ways better than the ordinary least square estimators, which we discussed in chapter 6. So in chapter 6, we have mu hat, which is a function of the projection of y onto v, and converted it to a beta, no? Which is a function of x prime x inverse x prime y. Okay, so let us recall with the simple mu hat that we had observed that in chapter 6, you have a y, which is normally distributed with a mean mu and variance sigma squared. Mu is v, which is p-dimensional, and sigma squared is positive. This is how we define mu hat, the projection of y onto v. And this is how this is supposed to be sigma squared, which is the square norm of the projection of y onto b perp divided by n minus p. So these estimators here are basic. The estimators that we are going to consider here are basically called or referred to as shrinking estimators, in that they modify your mu hat to make it into a shorter vector. So remember that if you have a vector y here, you can have a projection on that on your subspace V, no? So the projection of y onto b is this. So what we are doing here is to find another estimator instead of mu hat, which has a shorter vector or mas mubo siya. This type of estimator can also be extended in modifying your beta hat for estimating beta atong kini. But we shall concentrate of this form. Total, ma-derive lang maning if you have a mu hat, you can always derive the coordinatized version of the linear model. So we will just be dealing here for the coordinate-free version of the linear model. So the next lemma indicates why this is sensible. This is a sensible procedure. Or can we have a shrink vector, no, to estimate mu? Okay. So this is the lemma that talks about shrinking your mu hat to estimate mu. So remember, we are estimating mu by mu hat. So what James-Stein estimator do is they try to shrink. So ilan ning i-shrink ning mu hat. So if we want to shrink a vector, how do you shrink a vector? Kung na ako'y vector din kung saan ni nako pag-shrink or pagamayon siya.
I-divide siya, ma'am.
How do you shrink a vector? You have to pre-multiply this by a constant. Now that constant should be what? Dako, gamay. So
Gamay,
kung na
ma'am.
ako'y vector man, dapat na kay multiplier scalar din no? Para mo shrink siya. Kaya pwede man po nini mo i-expand ang vector. So if you have a vector can be expanded or can be kini ang y, pwede siya ipagamay or pwede po siya pataskon, no? So in your linear algebra, how do you expand or shrink your vector? Any idea? So you have to pre-multiply it by a scalar, no? Na scalar imong i-multiply para mo taas siya or mo gamay siya. So we will see that later how the James-Stein estimator is obtained. Now, this lemma tells you that the length na siya, no? The expected value of the length of your vector mu hat will be a function of a length of your mu plus some positive value. So ibig sabihin, if we are going to use mu hat as an estimator of our mu, and we try to get the length of this mu hat here, it is equal to the length of mu. So kung kini ang length sa mu, ang imuhang mu hat to estimate mu will be longer, no, by a function p sigma squared, no. So to show this result, recall from theorem 3.1b, you have this, no, that the expected value of the square norm of x, or actually the length of x, is equal to the length of mu plus the trace of sigma, where x is a random vector with mean mu and covariance matrix sigma. Also in theorem 2.5i states that the dimension, if the dimension of V is P, then the trace of PB is equal to P. It carries the dimension of RV. And note also that of how we define mu hat, again, that is the projection of y onto V. The distribution of the projection of y onto V will be normally distributed with a mean PB mu and a variance of sigma squared PB. So it follows, if we are going to get the square norm of the projection of y onto V, which is actually your mu hat, the square norm of your mu hat, using this, so you will have the square norm of mu plus the trace of the variance of mu hat, which is PB sigma squared. But this is a constant with respect to this PB sigma. So you can take it out and then just the trace of PB, but the trace of PB is equal to P, which follows the dimension of RB. So we have proven this lemma. So what is the implication of this lemma? The implication is that this lemma indicates that if we estimate mu by mu hat, or your PBY, we should be substantially overestimating the length of mu. So this is the result which gives James-Stein the momentum to propose another function of our mu hat, so that we can pre-multiply mu hat by a shrinkage constant, so that it will shrink. So kung kini ang length sa mu, no, o ni ang length sa vector mu, so ang iyang buhaton man mao ni ang pag-estimate nimo sa mu hat, mao ni ang mu hat. So ang iyang buhaton sa James-Stein is to shrink it, no? Shrink ang estimator, si kana mu hat si James-Stein, para mas duol siya sa actual length of our mu. Okay? So is that easy? How do we get the scalar component to multiply it with James-Stein still uses the information about mu, no? Still uses the information about mu hat to obtain mu hat hat. Okay, so we will see here how it is done. So for any estimator, say, mao na imong i-propose mu hat hat, it is possible to find a function of mu hat hat such that the expected value of that function of mu hat hat will be greater than a function on mu. So, mas dako gyapon ang expected value than or equal. Kung makuha niya, unbiased siya, it will be equal to a function of mu. Now, what makes lemma 11.1 interesting is that if P is large and this component here is small, so ibig sabihin if we try to look at this formula here, so if we try to standardize it with sigma squared, sigma squared, sigma squared. So if P is large and this one is small, ano siya, no? If P is large and the ratio is small, then we would be overestimating mu by a very large amount if we will use mu hat, no? So kung dako ang P, so kung mo nang iano, kung large ni siya, bahala pag small ni siya, ang expected value of the length bisan pa i-standardize nimo with sigma squared, it's still large because P is large. So what James Stein suggested is we might improve the OLS estimator mu hat by shrinking it. That is multiplying it by a scalar. So a scalar A, which is a function of mu hat and sigma squared, where this scalar is only between 0 and 1. So dapat between 0 and 1 lang, fractional, no? So to shrink a vector, mo to akong pangutana sa inyo, how do you shrink a vector? To shrink a vector, you have to pre-multiply that vector by a number between 0 and 1, because if you will get greater than 1, it will lengthen your vector, correct? You do not multiply it by a negative, kay what will happen to a negative? It will change the direction of the vector. Are you still with me?
Yes,
Yes,
ma'am.
ma'am.
So to lengthen a vector, you pre-multiply it by a scalar which is greater than 1. To shrink a vector, you have to pre-multiply it by a number between 0 and 1. Kung lengthen greater than 1. Of course, we do not consider the negative because it will change the direction of your vector. So it also suggests that when this component in your length is small, and this is using the estimate theta hat, and eventually, or it follows also, the over sigma, the original parameter will be probably small. Then a scalar which is a function, so dapat function siya of mu hat and sigma hat squared should also be small. So but when this one is large, then this one should be near 1. So it is either when this is small, you choose A to be close to 0. When this is large, you choose A to be near 1. Okay? So the challenge here is what will be the form of the scalar A, which is a function. Dili man na pwede number lang imong ibutang, no? It should be a function of mu hat and sigma hat square, and it should minimize the associated risk, no? Or the expected loss. So in this section, we look at estimator of this form. So mao ni ang nakuha ni James Stein na scalar. Forma niya is 1 minus C sigma squared, sigma hat squared over the square norm or the length of mu hat, where C is a constant. So dili ni siya magic na nanghangad lang sila sa atop, nakuha na dahil nila, no? So usually they try to manipulate the procedure first, look at the final answer and see what form mag-start na siya X, no? Mag-work sila sa proof using X and see in the final form what will be the form of X there to have a minimum loss or a minimum expected loss, the risk. And then once makuha nila ang forma dinhi sa X, ay na dahil na sila naglet na inaana ang forma sa A mu hat sigma hat square, no? So kung kana imong i-plug in, makuha na dahil to nila ang minimum risk. Do you understand? So in the proof, dili na siya magic na kabalo na sila ani, no? So they started with an arbitrary A, then work out the proof to look for these values, try to substitute some values there so that it will be satisfied, and then nakuha ni nila, and then nag-work lang dayon backwards dayon. So kung mag-let sila ani, kung i-plug in na nila ni sa ilahang proof, makuha na dayon to nila ang minimum risk. So the challenge here is, aside from getting this form, is 1 minus C sigma squared over the square norm of mu hat, the challenge also is what will be this constant C that will be minimum, that will give you a minimum risk. So ang James-Stein estimator will have this form. So always remember this, 1 minus C sigma squared over the square norm of mu hat, or the length of mu hat. So in the next subsection, we find the optimal choice of C, which leads to the James-Stein estimator. So as a standard for comparing different estimators, we use this loss function. So this is equivalent to your Mahalanobis loss function. If we will use the sigma hat here, this will be sigma over n. So what you will have here is n times d minus mu prime, and then sigma inverse, and then d minus mu, no? Mao man ni ang standard form sa imuhang Mahalanobis distance. Murag n d minus mu, di ba? Sigma inverse. Is this familiar to you? This is the Mahalanobis loss function, correct? You look at
Yes,
your
ma'am.
book. Okay, so equivalently sa univariate case, ang atong gamiton is sigma squared. Small sigma squared. So when P is equal to 1, the estimator mu hat has been known to be admissible. So when P is just equal to 1, mu hat is admissible, or mu hat, which is the PBY, is admissible. When P is equal to 2, admissible gihapon si mu hat. However, the problem comes when P is greater than 2. Mu hat becomes inadmissible. So in line with this, James-Stein in 1960 exhibited an estimator that is better than mu hat when P is greater than 2. So to see this, let an estimator D, a function of Y, no, be an unbiased estimator of mu. So unbiased estimator, one candidate of that, your estimator is your Y bar, because we know that Y bar is an unbiased estimator. So this will be a mu hat, no? But James-Stein proposes another estimator for mu let me call that mu hat hat, which will give you a shorter length of mu hat hat to estimate your mu. So recall in chapter 6 na kinina mu hat nato na y bar is also MBUE, no, for mu. And then to be able to prove the next theorems, we need to recall theorem 1.5 of Arnold's. So tungod kay 1.5 na nasa chapter 1. So suppose we are estimating tau of theta. So mangita tau of theta hat, no? Mga estimators ni siya to estimate a function of theta with a given loss function d and theta. So it tells you that kung naa kay function sa imong x and that function is a sufficient statistic, and you have another estimator, say t of x, so another transformation. So to see this, mura siya ani. Kini ato ang a function of x can be the summation of xi. And kini ato ang t of x sufficient pa na. Kana atong t of x mo ni si summation of xi over n, no? Are you with me? So napakita man nato kanang summation of x sufficient statistic na siya. A derivative of another derivative of x can be obtained by getting the average, no? So you divide nimo by n. Of course, that is also an estimator of tau of x. So if you can have another statistic t star of s, bale, a function of a sufficient statistic, no? And it is just equal to the expectation of this estimator, kanang t star is equal to the expectation of this estimator given s. And then if the loss function is a convex function for all d, convex is saan convex na itsura sa if you have a convex function, it looks like this, no? If we plot for all theta, no? Convex. Concave man ang out. Can you let me just have the cell phone. So I'm not sure kung ang convex monotonically decreasing or increasing. Let me check. Convex function. Properties. Okay, so it's monotonically increasing, no? So a convex function is monotonically increasing function. So paano siya, no? So if you have a loss function that is convex, so either it is increasing with c greater than or equal to 0, it is concave when c is less than 0, and so on and so forth. So naay mga properties ang convex function. So kung ato ang loss function is a convex function for all d, for all theta, then kining imong nakuha na estimator, which is a conditional expectation of your t of x given that sufficient statistic, is as good as your t of x. And if moreover t of x is unbiased, then also t star of x, or the conditional expectation of t of x given a sufficient statistic, is also unbiased. So let me explain first what is A. So This is only true if our loss function considered in this discussion are convex function. Ha? Ang loss function is a convex function. So theorem 1.9a implies that for any estimator, there is an estimator based on a sufficient statistic that is as good. No? So, which is as good as your T of X. Kana imuhang let. So this reinforces the idea that nothing is lost if we reduce the data to a sufficient statistic. Okay, the next is if you have a complete sufficient statistic and you have a function of that complete sufficient statistics, which is an MVUE for tau theta, then if your loss function is convex for all d in theta, then your T of S is also as good as any unbiased estimator for theta. So what is the meaning of this? It tells you that theorem 1.9b implies that the minimum variance unbiased estimator is the best unbiased estimator for any convex loss function, since it is as good as any other unbiased estimator. So, ibig sabihin, si y bar kay unbiased MVUE for a given loss function, any function of your y bar is also unbiased and is also have the same properties as your y bar. So under this loss function and by this theorem 1.9, our mu hat, which is the projection of y onto v, which is by formula is 1 over n the summation of yi, is as good as any other unbiased estimator. Hence, to find estimator that is better than mu, most likely unbiased siya or dili unbiased? Or bias siya? So kung mangita tag any other estimator better than mu, we must look outside the set of unbiased estimator. So we will expect that this mu hat sa Jamestown will be a biased estimator. So kay kung mutanaw lang ta sa set of unbiased, wala na makalupig ni y bar because any function of y bar is also as good as y bar. Kung i-complicate pa nimo siya i-complicate pa nimo ang y bar na unbiased mangyapon siya. So MVUE naman si y bar. So wala na tay makitaan sa set of unbiased estimator. So what we will going to do is we look outside the set of unbiased estimator. Also, since mu hat is inadmissible na, so all unbiased estimator are also inadmissible. For ano sa gani ni siya inadmissible? For p greater than 2. It is admissible at p equal to 1 or p equal to 2, but for p greater than 2, mu hat is already inadmissible. So similarly, in chapter 6, we showed that mu hat is the best invariant estimator. So therefore, all invariant estimator must be inadmissible when p is greater than 2. So dili na pud ta pwede mo tan-aw atong set of invariant because for kay si y bar invariant man na siya. So any function of that will be invariant and it will be inadmissible for p greater than 2. So an estimator that is better than mu hat could not be invariant. So kining Jamestown estimator will not be unbiased. It will be a biased estimator, but it will have a shorter it will have a smaller risk or expected loss than mu hat. Later we will see. And it will not be an invariant estimator and it will not be an MBUE. So it is a bias with a minimum risk. A risk which is lesser than mu hat. So we did not yet computed what will be the expected loss or what is the risk function when using mu hat. So in the next lemma, we will try to prove what will be the associated risk when we use mu hat. So ang atong ma-compare lang ani si mu hat against mu hat kanang Jamestown will be in terms of a risk. We will not be able to compare it with respect to unbiasedness because the Jamestown will be a bias. Okay, ang best na unbiased si Y bar jud or si mu hat, no? And then the best invariant si Y bar gihapon. Pero in terms of admissibility and inadmissibility, admissible lang si Y bar for P equal to 1 and 2, but for greater than 2, it will no longer be admissible. It becomes inadmissible. So let's have first a break, a 10 to 15 minutes break before we proceed with lemma 11.2. So lemma 11.2 talks about the risk or the expected loss associated when using mu hat as your estimator. And it is equal to P, which is the dimension of your space, V. No? So recall that Y bar or the one that we are going to use. So this should be Y bar. No? The risk associated when using your Y bar is normally distributed with a mean mu and a variance of 1 over n sigma squared. And by theorem 3.10b in chapter 3, you see there that Y bar minus mu, what you see there is something like this, no? Y bar prime, Y bar minus mu. Now our sigma in this scenario will be 1 over n sigma squared because the associated estimator that we are using is Y bar, is chi-square central with p degrees of freedom. So we see that Y bar minus mu and Y bar with a covariance matrix 1 over n sigma squared is chi-square distributed. And we know, of course, this can be written as n Y bar minus mu prime sigma squared inverse and then Y bar minus mu. So this is chi-square distributed central. And we know that for a chi-square distribution, if you have an x which is chi-square distribution with n degrees of freedom, then the expected value of x will be equal to the degrees of freedom. So in this case, if you get the expected value of this variable here, which is equal to this, the expected value there will be equal to the degrees of freedom P. But if we look at this formula, we get the expected loss. This is how we define our expected loss earlier, mu squared over sigma, but our sigma for a Y bar is 1 over n sigma squared. Are you following? This is our associated loss function. So if we get the expected of the loss, that will be our risk. So if we get so this is a result when using the information that this term here is chi-square distributed, but this term here is actually the term inside there, So if it is chi-square distributed, that is equal to P, the expected loss by formula is the expectation of this term. So that is D minus mu over sigma squared, but our sigma squared is 1 over n sigma. Our D is the y bar, and our parameter is the mu. So if we try to rewrite that, that is actually equal to this. And that is the risk associated with using y bar, and that is equal to P. So it means that expected loss or the risk associated when using y bar is equal to P. Okay, any questions? Do you understand?
Yes, ma'am.
Okay, so next we find another estimator whose risk is everywhere smaller than P. So para mahimot ang competitive, dapat ang mangita ta. So our mu hat is y bar. The expected loss or the risk associated when using y bar is P. So what we want is to find a mu hat hat, which is just a function of mu hat, but we'll have a risk which is less than P, no? Para may mo siyang competitive. Okay, so when mu is 0, when this one is equal to 0, and we try to compute for a P, okay, kini siyang y bar, asa ra gani ni siya admissible when P is equal to 1 or when P is equal to 2, no? When P is greater than 2, dili naman siya admissible. So atong expected risk dapat about 2 lang, no? Kay diha man siya maayo. Otherwise, if P is larger than 2, then this estimator is much better. So therefore, if P is much larger than 2, this estimator is much better than mu hat for mu is near 0, or moderately better than mu hat. This is done when this ratio here is large. So it has something to do with the expected value of the length of mu hat, no? So to do that, we have to state first the following lemma, because this lemma will be used when proving or finding the expected loss associated with the Jamestown estimator. So we will just state this lemma. So if we will have a U, which is normally distributed with a mean theta and covariance I, and K, we'll have a Poisson distribution with this mean square norm of theta squared over 2, then the expected value of the inverse of the length of U, where U here is normally distributed, will be equal to this, no? Equal to the expected value of 1 over P minus 2 plus 2K. And the expected value of U prime, U minus theta over the length of U, will be equal to the expected value of P minus 2 over P minus 2 plus 2K. If you want to see the proof of this, this is found in Arnold, the book. This is lemma 11.3. I did not write the proof here, but you can check chapter 11 for the details of the proof. So what I want to emphasize is how do we derive an estimator which is better than mu hat. So to derive that, we will use this estimator, or this is actually the constant na atong i-multiply, no? you recall, this is the constant that we want to multiply, which is, this is the constant, which is a function of mu hat. So this is the scalar. So gitawag na niya, kaya ang scalar raman ni siya kinina forma kung ang a function of mu hat gihapon, that will be the estimator. Let us originally call it as dcy, or a function of y, or an estimator that is dependent on C. Morning na I see no, it is dependent on a value C there that we have to find out pa later. What will be the value of C that will minimize the risk? So in general, you have an estimator which is a function of mu hat, which is pre-multiplied by this scalar. Note that if C is 0, then your estimator is just your mu hat. Now, since this estimator is random, scalar siya times mu hat, any transformation on your mu hat which is in V is also in V, no? Because V is a subspace, no? So close siya under linear combinations. So now we have to find the risk of D. Remember that the risk associated with Y bar is P, and we want to, this is your mu hat, we want to find an estimator wherein the risk associated with this estimator should be less than P. So the next lemma tells you that the risk associated when using this estimator will be equal to this term here. So now, can you say in this, by this formula, that this is smaller than P? Is this smaller than P? Look at this formula. Is this smaller than P?
Yes, ma'am.
Why?
Kay mag-minus man, ma'am, og some terms, ma'am, from P.
Oh, but you have to be assured that this term here is positive, because if this is negative, then this will be greater than P. Are you with me?
Yes, ma'am.
So in the proof, you have to assure the reader that this term is positive and this term is positive, because if one of them is negative, then it's no longer less than P. Okay? So it's yes on the condition, no? So be sure that before you answer, make sure what should be the condition that this should be less than P, not just a yes answer. Are you following? So in the proof, you will expect somewhere that to show that these two terms here should be positive, because if one of them is negative, then that will be a problem. And if both of them is negative, is that a problem? If both of them are negative, will it be a problem? Yes or no?
No, ma'am.
No. But can we expect these two terms to be negative? Can this be negative? Can this be negative?
If P, ma'am, is greater than N?
Since this is a function of a K which is Poisson distributed, what will be the range of a Poisson distribution? So if you look at the previous lemma here, you have a K which is Poisson distributed. And P is assumed to be greater than 2. Else, kung less than 2, maayo man ang mu hat na. So if P is assumed to be greater than 2, this will always be a positive thing, no? Or a positive term. Poisson takes on values on positive. So I think the scenario that both of them are negative is not feasible. And in here, V, which is an element of RP, is always a subset of N. So ibig sabihin, N is always greater than P. Are you with me?
Yes,
So
ma'am.
wala tayo condition na mahimo ni siyang negative. Okay? So in the proof, we have to really verify that these two terms here are positive terms for it to be less than P. So let us look the flow of the proof here. So we know that sigma hat and sigma hat square are independent by this theorem, theorem 5.1. Then the conditional distribution of, since they are independent, sigma hat square given mu are the same as the marginal distribution of mu hat. So when we apply lemma 11.2, katong the expected loss or the risk function of this term here will be equal to, so ibig sabihin, it doesn't matter with the conditional distribution, okay, it's just equal to the marginal distribution of sigma hat, so that we know that the distribution of sigma hat will be chi-square with this transformation, no, n minus p sigma hat square over sigma. And when we use mu hat, the risk associated with that is P. We have shown that earlier. Okay, so these are known facts or known results. And another mostly verified in probability courses, you should know that the expected value of sigma hat square, okay, so this is actually a denominator which is n minus 1. This is an unbiased estimator, and this is the fourth raised to the fourth. You can verify this to be equal to n minus p plus 2 sigma to the fourth over product. So actually, ang mahitabuan ni this is a product moment, no? So let us suppose we know this from probability courses. And of course, this is an unbiased estimator property. And now we define an orthonormal basis for V. And define U to be equal to, for simpler notation, to be equal to 1 over sigma x prime y. Then the expected value of U, we call it theta, will be 1 over sigma x prime mu, because we know y is normally distributed with a mean mu. So we have two terms here, u and theta. Theta is the expectation of u. And the covariance of u will be equal to the covariance of 1 over sigma x prime y. This is just a constant. And then the covariance of x prime y, this is similar to what you have, the covariance of ay, no? The covariance of ay is, unsa gani? A covariance of y a prime, correct? So if we use this, so you will have x prime covariance of y x prime prime. But the covariance of a y is sigma squared. So this is cancelled with that. And we know that if x is an orthonormal basis, then x prime x is I. That is a result in chapter 3. Are you with me?
Yes, ma'am.
So we can conclude now that the distribution of RU, this is RU, the distribution of U, which is 1 over sigma x prime y, is normally distributed. This time, it will be p-dimensional because this will be a p by p matrix x prime. So this will be p by n, then n by 1. N by 1. So you will have p by 1. So it's p. This is in the univariate case, no? So it's a vector pa. So if this is how you define your U, this is the distribution of U. Now, since mu is in V, so mu, which is PB mu, it's just equal to PB mu because mu is in V. PB, if X is an orthonormal matrix, is XX prime. No? Ang X prime X, mauna ang I, pero ang XX prime will be PB. Are you following? But x prime u, this one, x prime u, is actually sigma theta. X prime u is sigma theta. So what you will have is x sigma theta, but since sigma is just a constant, you can write it as sigma x theta. So you have that. So your mu is sigma x theta, and then your mu hat, which is PBY, but PB is x prime y, and then since x prime y here is just sigma u, no? So x prime y is sigma u, so this becomes x sigma u, but this is just a constant here, so that's sigma xu. Okay? Are you still with me?
Yes, ma'am.
So this is sigma xu. Okay? And if we try to find out what is the length of u mu over 2 sigma. So dinhira na gikuha, you have a u there, divide it by 2 sigma squared, get the square norm. So what you do is get the square norm of this, then divide it by 2 sigma squared. So you have this, and then you do some manipulation. This one will just be equal to this. Similarly, 1 over mu hat square. Mu hat is this, which is equal to this. So get the reciprocal of that, get the square norm, simplify. So you will get this one is just equal to this. And this one, by manipulation, you can check this, will be equal to this. So we transform mu hat now in terms of u and theta, no? So this is just cancelled with this. So may muna siyang mu prime, and this one is cancelled with this. May muna siyang mu prime u, which is the square norm of u, and then you have u minus sigma prime and u. So what is this saying is that we can easily transform from mu hat to an estimator in terms of x prime y, no, which is u. So this is your u. So from mu hat, you can easily transform it in terms of u, which is in terms of x prime y. So ang mga mu din can be in terms of theta, in terms of u, and this transformation in terms of u. So that is the emphasis of these derivations here. So that using lemma 11.3, this one, finish siya. We have shown that U is normally distributed. And then if we have a K, which is Poisson distributed, you can have these results. So applying that, after this transformation, you have this, no? So this is the letter B, which we can write it in this manner. And this is equal to that expectation. So this is B and this is A. So now we get the risk associated with DC. So what is our DC? So how did we define DC here? Sure. Siyang reviewhan. So akong DC. Okay, here. So what you have here is mu hat minus mu hat C sigma squared over the square norm of mu hat. So we get the risk associated with this estimator. So mu hat, or equivalently, that is your what? Y bar. So the risk associated with that is P, no? And then so to mu hat minus mu hat C sigma hat squared square norm of mu squared. Diba? Hat. Okay, and then these two terms will be expressed in this manner. So ibig sabihin, this part here can be expressed as the sum of two expectations, one and this one. So ang isa So let me write this as mu hat minus 1 over the square norm of 2. Mao ni siya. And then ang isa is times, okay, let me have some space. So ang atong DC is mu, ang atong DC is 1 minus C sigma hat square over the norm of square mu, no? But this is equal to mu hat minus C mu hat sigma squared over square of mu hat. And you can write this as mu minus 1 over mu hat square times mu hat C sigma squared. Okay? Okay, so this component here, the risk associated with that is P, and this will be this term. And then this will be this term, no? Mare-write na nimo inani na itsura. So diretso na ko anak because there will be manipulations in doing that. So what you see here is a component of this, man kini ang component para ani, and then kini ang component para ani na itsura, no? You can subdivide that in that manner. So that what you have is, this is the risk associated with using dy, which is 1 minus C sigma squared over the norm square, mu hat, okay? So we need to check that this is positive and this is also positive. So we need, and we also need to find out what will be the value of C, because this is still a function of C. So now we need to find C that minimizes the risk. So if P is greater than 0, this is always positive. So we expect this to be positive. And then N is always greater than P. So this term will also be positive. So how do we find now the C? Here. So if you recall in your calculus series, what you have to do is, for it to be minimized, you get the derivative of that with respect to C, and then equate that equation to 0 and solve for C, no? So for C after equating that to 0. So if you get the partial derivative of the risk with respect to C, so derivative nimo sa C, partial, because you can always get the derivative with respect to other random variables there available in the equation. So if we get the derivative with respect to C, this will be a constant with respect to C. So may mo na siyang 0, and then this has a C there. So derivative of C is 1. So mabilin 2P minus 1. And you have a C squared there. So ang mabilin ana is derivative of C squared is 2 times C. So you have 2 times C, and this will be a constant with respect to C. And then this constant there. And then you equate that equal to 0. All other terms will just be a constant, and cancellation, and solving for C alone will lead you to this, no? So I will not do the algebra. You do the algebra, you will arrive at a C equal to P minus 2. Actually, mao ni siya, kana siya, makancel lang na siya. And then kini siya musaka, N minus P, and then N minus P plus 2. This is the C that will give you a minimum risk, so that the proposed James time estimator for mu now, i-substitute to nimo dito, di ba? Ang dcy is 1 minus c sigma squared over the square norm of mu hat squared mu hat. Substitute the c here, which is equal to this. And this is your James time estimator. So we see that the risk is smaller than P, no? So comparable with your y bar, which is just equal to, or our mu hat, which is just equal to this formula, and compare it with this formula, di ba? Ang balik na lang ko sa unbiased, ay inani ang itsura, bias pa yun siya, no? But it's a balance between a bias but with a minimum risk, no? Because the risk associated in using this estimator is lesser than the risk associated with mu hat. And the risk associated with this will be equal to, so upon substitution it with this general formula. So mao man ni ang general formula, no? If we use a form of an estimator with 1 minus something mu hat, mao ni ang general form. Now once we get the C for that, this is now the risk associated when using your James time estimator. No, you just substitute C there. You just substitute C there and simplify, and you will get this risk. Of course, it is a function of K because along the way you prove the risk using some results on a K, which is Poisson distributed with this mean mu. So in particular, when your mean is just equal to 0, your risk associated when using your James time is 2n over n minus p plus 2. So when p is exactly equal to 2, the risk associated when using mu hat will be 2, which is just equal to the risk associated when using mu hat, which is p, which is 2, no? So, kung ang minimo is just 0, so ibig sabihin ang imong mu ba na central, standard normal lang, nasa mu equal to 0, the James time estimator is as good as the y bar. And in terms of formula, y bar will be better. So that is when P is equal to 2, because the associated risk here will be equal to 2. Do you follow? Kung standard normal lang mu, no? Then that's why we always use y bar instead of the James time. Dili siya popular. Do you hear me?
Yes, ma'am.
For bivariate normal distribution, y bar is still popular. Univariate labaw na. Aside from NBUE, invariant, and MLE, admissibility, y bar is enough, no? So the risk associated when mu is equal to 0 follows when we substitute C in the formula in lemma 11.2. And this theorem establishes mu hat hat is much better than mu if mu is near 0, and somewhat better for all mu, especially when P is greater than 2. Note that the risk associated with your James time depends on the mu and the sigma only through this mean. So what if dili nimo is shrink towards 0? nakakailain na mean because it's not always the case that your normal distribution is standard normal. But then again, ang usual na ginabuhat sa multivariate na statistical methods is to make it standardized. Gina-transform nato ang atong mga variables to have a mean zero, no? The advantage of the Jamestown estimation is it may not be necessarily that you shrink it towards zero. You can always get a vector V wherein you define a Jamestown estimator that you will shrink it towards V. But the formula now, instead of mu hat square, you have to get the square norm deviation from V. No? So, murag yapon i-transform nimo into a standard normal. Okay? So, actually, if you put this down, mahimo naman na siyang mu hat minus V over sigma square. No? So, it's just doing standardization. So comparable lang si Jamestown when we shrink it towards zero. But if we have a different value for our mean or towards V, then Jamestown will be better off than our usual Y bar. And then the risk associated now when using the V hat hat shrinking towards V will be equal to this. Okay. So let me read these remarks here. Therefore, mu hat hat V does very well if mu is near V. If mu is near zero, then comparable lang si Y bar o si Jamestown because the risk associated for both of them will be equal to approximately equal to 2. But the mu hat hat V will be better than mu for all mu. This fact furnishes an interesting aspect of Jamestown estimation. A researcher can choose a value V that he thinks that mu should be near. He can then compare mu hat hat V. If he is correct, mu is near V, his estimator is much better than mu hat. But even if he is wrong, his estimator will be better than the minimum variance and bias estimator, that is your mu hat. He must of course choose V before he looks at his data. This aspect is also a disadvantage of Jamestown estimation, in that two different experimenters would find different estimators from the same data if they choose to shrink on a different point. So, depende sa asa siya paingon mo shrink, no? On V. The Jamestown estimator has sacrificed the objectivity of the ordinary least square estimator. In addition, on a particular experiment, a researcher may have no idea where mu is, no? So, that's the disadvantage that we see in the Jamestown. In that case, there does not seem to be any obvious way to determine a point to shrink forward. Okay? So before I will go to the multivariate case, let's again have a break, 10-minute break. So now we look at the Jamestown estimator in the multivariate case. So the concept is similar to your univariate case. We still have to compare your the length of Y bar. So Y bar now will be a matrix now with respect to a random matrix. Here we have N will be greater than R, greater than 2. So our estimator now will be Y bar, capital Y bar, which we define in a usual formula, but this time each of these are vectors. And if we look at the expected length of y bar, it is equal to the length of your true parameter mu plus some term here, which is 1/n times the trace of sigma. So if you recall, in the univariate case, we had mu hat, the length of square there was equal to the square norm, the length of mu plus, di ba, p sigma squared, no? Correct? This is the trace of your sigma, of your PB. Now this time we will have a division from p sigma squared. So we retain the trace, which is just equal to the trace of sigma times 1/n. So for the proof of that, you still follow the technique which I introduced to you, which is adding and subtracting mu there in your term, and then use the property of square norm. So that is mu prime mu, get the expectation. The middle term will just be equal to 0. So this is the final answer there with these assumptions on your y bar. So you can go easily through the term and use the properties of the trace. So lahi lang ang style of proof niya because what we will be using is some properties of the trace and some matrix algebra. So as a comment, this equation suggests that if we use y bar to estimate our mu, we are substantially overestimating mu. It seems that we would be able to improve y bar by shrinking it. So this is what I was telling you about in the multivariate case, univariate case. And then again, since we will be comparing y bar with a Jamestown estimator, we will be looking at the expected loss, and the loss function that we are going to consider here is the Mahalanobis distance between mu and its estimator. So this is your Mahalanobis loss function. So for r equal to 1, again, y bar will be admissible. For r equal to 2, y bar is still admissible, but it becomes inadmissible when r is greater than 2. So in the multivariate case, we use the variable r instead of p. So what did James and Stein do is to derive an estimator that is admissible for r greater than 2. But then again, since y bar is invariant, unbiased, so this new estimator now is not invariant. It cannot be invariant. It cannot be unbiased also. So it's a bias estimator. So if we assume that r is greater than 2, of course, n is greater than r, so that this can be justified that sigma inverse or S inverse is existing. Okay, so in the univariate case, we have shown that the risk associated when using mu hat to estimate mu is p, that is the dimension of your subspace V. Here, we will use the notation R. So the concept is still the same. We know that y bar is distributed in this manner, and a result that has this conversion is chi-square central. And then if we have a chi-square distributed, you get the expectation of this that is equal to the degrees of freedom, which is r, But we know that this formula in the inside is actually the risk associated when using y bar. So the risk associated when using y bar is R. So this is actually the expected loss function. So similar scenario except for notations, no? We use bold letters here to identify that it is now, we are now dealing at multivariate matrix. So the estimator now, if you look at this, can you recall unsa to atong estimator sa univariate case? Our DC there was just 1 minus C sigma squared over the square norm of mu hat, no? Are you still following? So dinhi na si C pero si sigma square na sa ubos. Okay? So actually pwede po na siya sa taas. But then again, we here pwede ra nato itaas because that is just a scalar. But in this case, we will use the y bar prime S inverse y bar. Are you following? Na siya sa ubos. Katong sa univariate na pataas to nato because this is just a scalar. Okay?
Yes, ma'am.
Inani gyud ang forma pag multivariate case na. We will have, because the Mahalanobis distance will have this form. Sigma inverse. So dapat na siya din. Are you with me?
Yes, ma'am.
Okay. So we still have the results with respect to a random variable k, which is Poisson distributed, but this time it is with this mean mu. Ang katong sa univariate case, ana ra to siya, no? Square norm over 2 sigma squared. Correct? And this time na siya din. Okay? So there is some slight form, but more or less they have the same variables under consideration. And the risk associated by using this type of estimator here this one will be R times this one and this one times the expected value of this. So we will be assured that this is less than R if all of these terms here are positive, no? So wala tay problema din that is plus something, but kini siya dapat gamay siya, no? For it to be a positive number. So along the way, we have to prove that this term here, this is always positive. So we have to show that this term here is positive, because if that is negative, then everything will be R plus something, no? So in the proof, the author has shown that this term there is also positive. So how do we show the risk associated with DC, or DC is of any estimator of this form? We still use the property that y bar and s are independent. The distribution this time is no longer chi-square, but you use the generalized chi, which is Wishart with this estimation. So that this form here will have a chi-square distribution for y bar. S is Wishart. Y bar with this transformation, so that when you get the expected value of our statistic D, di ba, mao ni ang formula, no, sa atong statistic D, expected loss. This is the expected loss, the loss function associated when using your D. And then you do some manipulation. What happened here? Your DC is your Y bar. Y bar, sigma squared. This part here is the form of your estimator. No? What is your estimator? Your estimator is Y bar minus CY bar over Y bar prime S inverse Y bar. So this is your estimator. That will be your DC substituted here. So this is everything here minus mu. The group lang nato ang mu. Are you following? Are you with me?
Yes, ma'am.
Yes, ma'am.
Kini siya, kana siya ang mu, no? Kanay siya, mao na imong DC. Okay? That is your DC. So DC minus mu. Okay, Ra?
Yes, ma'am.
That is DC minus mu. Pila ka kape na inyong nahurot? Nadili mo matulog. Wala ra ma'am, usa ka stick ra. Okay. So up to this part, this is okay. And then what happened? Distribute na ni siya, no? Expectation, ani. Kini man tanan, expectation, ani. So nakakay term na ani, kining tulo. Are you with me? And then kana o kana, man kini o kini, o kini, man kini o kana. No? Kana, mura na butterfly. Okay. Kani, kani, kani. Mao na term. Okay? And then sunod. Ang kining 2C, mao ni siya na term. Kini, og unsang isa. Kini, og kana. Man kini siya, isa na to color. Kini siya, unsang na siya. Kini siya, kana, og kana. Okay? So that's why you have C square here. It's just algebra. Are you still with me? So
Yes,
there are
ma'am.
4
Yeah.
terms, but the 2 terms will be joined by this. Okay? Oy, napa mo diha?
Yes, ma'am.
A minus
ma'am.
B man C. A minus B, di ba? Ano man na oh? A squared C. Oh, basta kabalo na mo anak. Algebra ram na. So 3 terms na lang siya kay gi-join ang duha ka middle. Mao ni siya. Pareha raman silang itsura. Okay? Next. You try to simplify the second term. So, kini na term. Simplify this. So, ang simplification, kamo na itanaw ha. And you can do expectations of XY, expected sa X, expected sa Y because of independence. Morning na ay expectation, product of 2. And then you have this after simplification. And then look at the third term, which is this one. That is the third term. Look at this. Simplify. Again, use independence of y bar and sigma, no? Y bar and sigma. Use the property of that, and the third term will be simplified at that, as that. Okay? And then the first term is as is. And note that this term here, this term here is true because of this property, no? Kini na part, kini. Kini siya, no? Get the expectation of that is equal to that. The variance of a chi-square, which is equal to the degrees of freedom times the expectation of a chi-quantity square, which is degrees of freedom square. Okay? So what is this doing? This is doing this. So now you do substitution of what you derive from the from the second term and the third term. That was just algebra. I expect that you know how to do it. So this is the first term. This is substitution of the second term after simplification. And this is substitution of the third term after simplification. And then you do algebra again. Combine like terms, simplify. This will boil down to this equation. So this part here is simplified in this manner. And this part here is simplified in this manner. Okay? And then we do similar thing as we have done. Katong nag-define dito ta sa U na 1 over sigma x prime y, no? Inomdo mo sa univariate case. And then show that it is normal so that you can use unsa ganito atong gamiton katong lemma, no? Pangitaon nato si u minus theta. Pangitaon nato si u prime u minus theta. That's why I discussed the univariate case kay masayon, and then ma-extend ra ninyo sa univariate case so that you can write this quantity in this manner. Manaana dayon katong lemma 11.3. And then you can write this term into 1 minus u prime u. So ato na i-convert. Gamito nimo ang lemma 11.3. Mao na dayon ni. Mao ni ang expectation katong kini siya sa univariate katong 1 over the square norm of u squared, no, equal to the expectation man. Letter B ni siya, no? Kini mao ni ang letter A na itsura. Okay? That's the multivariate scenario of it. So that the risk associated when using a D, sa ito itsura sa atong DC, atong 1 minus C something, no? Y bar, sigma inverse Y, Y bar. Okay? The risk associated of using a form of that will be equal to this. So the challenge is, sa challenge ani gani na nakaani na risk function associated with this. Unsa gani ito'y challenge?
Value ma'am sa C.
Okay, the value of C, and to check that these terms are all positive, no? Because if this is negative, problema ta, no? Because that will add. So what we do is to check that it is positive all the way. Okay, so this is what this next line is doing. And then again, correct si Maaghop to ni answer, no? Or si Ganob?
Maaghop ma'am.
Okay, si Maaghop, the challenge is to find the value of C that will minimize this risk. Surag si Maaghop lang ang nakainom og kape rong adlaw. Okay, ano na ninyo? Put panda na ng mga kape diha para mata. Okay? So, is there a difference with the univariate case or with the multivariate case of the itsura sa C? Do you see a difference? That is the C for the multivariate case. I don't want to scroll back, so I will just look at the book. What is the C associated with the univariate case? So, this is the difference. This is for the univariate case na C. C is equal to P minus 2 N minus P over N minus P plus 2. Recall that P here is R for your multivariate case. R minus 2, okay? No? But this time you have N minus P, but it's N minus 1, but you have an N here. And then, pareha na sila din here. Okay? So that's the difference here. This is for memorization scenario, no? Kung sa diferensya nilang duha. Okay? So that is your P. What is the next step? The next step is to define your estimator, James Stein, by substituting C in the formula of DC. No? So substituting C in the formula of DC, you have your James Stein estimator. Okay? So this is the one that will yield the minimum. And then if the risk associated now when using your James Stein will be equal to this, but since this is a positive term, then it will be less than R. And when mu is 0, the risk associated when using this is just 2n over n minus R plus 2. Comparing it with the univariate case, the risk associated when using mu hat is 2n over n minus going back. It's 2n over n minus p. Parehara. Plus 2. Except that we are using R for the multivariate case and P for the univariate case. Okay? So to prove that, you just substitute C in the risk associated with using the James Stein. And this is always positive. So that will assure us that the risk associated with using James Stein is lesser than R. Because R minus a positive thing will be smaller. So if it is at 0, central, mean, at 0, then ano lang, more or less the estimator associated with James Stein is just equal to the risk associated with Y bar, approximately 2, because ang risk associated with Y bar is equal to P man. So kung P is 2, parehara sila. Are you following? No? Hello, class? Are you still with
Yes,
me?
ma'am. Yes, ma'am.
Of course, we do not shrink it about 0. The advantage of Jamestown is you can shrink it in other values of mu, say v. So, pero there will be some readjustment that you are going to do. You still centralize it or square norm it with from the difference from v. We call it mu v. So it's the same concept as in the univariate case. You have to make some adjustment, okay, on your y bar. Subtract from b plus b there, and then adjust it here also. Transformation on your wrist. But the advantage is that there is associated with making a new estimator with respect to a new shrinking origin. It's just the same as the original Jamestown, except that you adjust it mu minus b. So scale invariant siya. Bale, dili mausab, no? And then it is also but it is not invariant with this transformation. It is invariant with this transformation. In general, dili siya invariant, pero kung inani imong transformation, invariant siya. And then this will be the complications now if you really want to adjust further depending on your v, no, greater than your mu at greater than 0 or less than 0. But in general, the Jamestown, you can always improve it to be a better estimator than the Jamestown. So kung na kay Jamestown, man imo nang i-better improve by some transformation, mahimo po good siya better. So that's the advantage. But then, it's a bias estimate. Okay? So in anak kapaspas ang multivariate case once we already discussed the univariate case. That's why I decided to do a notes on the univariate case para mas dali ra mo makafollow sa multivariate case. Okay? So that's it.